Now it's my privilege to introduce our esteemed speaker for this session, Dr. Akshay Verma. Dr. Akshay Verma is renowned glaciologist and environmental studies, currently serving as a scientist C at the Center of Cryosphere and Climate Change Studies, National Institute of Hydrology, Roorkee. He specialized in glaciology, isotopy hydrology, and environmental change with over a decade of field experience in the Indian Himalaya and Antarctica. Sir has completed his PhD in environmental science with specialization in glaciology from Doon University, Dehradun, focusing on isotopic and geochemical signature in glacier. Sir has completed the MSc in Environmental Management from the Forest Research Institute, Dehradun. Sir has completed the BSc in Environmental Science from Maharaja Sayajirao University, Vadodara. Sir has the various professional contributions are lead to hydrometeorological monitoring of key glaciers, including the Gangotri, Dokriani, and Mila. Sir has established the meteorological and hydrological observatories in the remote Himalaya regions. Sir has conducted the bathymetry studies of dangerous glacier lakes in collaboration with the Uttara State Disaster Management Authority. Sir has contributed to disaster response during the Chamoli disaster in 2021, providing the initial assessment report to national agencies. Sir has proposed the integrated multi-hazard warning system for disaster risk reductions. Sir has the various key contributions are awarded the Best Research Paper Award twice in 2019 and in 2021 at the Wadia Institute of Himalaya Geology. Sir has contributed to the assessment of glacier, shores, and hazard using the remote sensing technology. Sir has supervised multiple master dissertation and internships mentoring the future scientists. Dr. Akshay Verma ongoing contributions are his focus on glacier hazard, hydrology, and climate change impact in the Himalaya regions, and his collaboration with the National International Organization for Glaciology Research and Disaster Management. Sir has recognized for the critical insight into the glacier dynamic environmental process and contribution to sustainable water resource management in the changing climates. Thank you, sir. We are honored to have you with us, Dr. Akshay Verma, and look forward to your valuable insight. Over to you, sir. Thank you, sir, and welcome to the Bharati Vidyapeeth College of Engineering for Women's, Pune.
Thank you so much.
Thank you, Yesugure sir. You have done a splendid introduction of Dr. Akshay Kumar Verma. But I like to do the one correction that we are doing this FDP collaboration with NIH. So
Yeah.
we had not mentioned. So that was the thing. Yeah, sir, Akshay sir, you can continue. Thank you.
Yeah, thank you so
Okay,
much
sir.
for the wonderful introduction. And I'll just share my screen.
Yesugure sir, stop sharing, then he will.
Sir, you can share your screen.
It's visible, sir.
Okay. Just is it visible?
Yes, sir, it's visible.
Yeah.
Yes, sir.
A very good evening to everyone. I'm Dr. Akshay Verma. I'll be talking about cryosphere and its monitoring in a warming climate. And so, as you can see, the first picture itself, this is Chorabari Glacier uh, uh, behind Kedarnath Temple. And so, the first question which comes to our mind is, what is cryosphere? So, cryosphere is basically the frozen water present on Earth, and it includes snow, glaciers, ice sheets, ice caps, permafrost, sea ice, lake ice, river ice shelves, icebergs. So everything, any form of water which is frozen comes as part of the cryosphere. So why is it important? It provides fresh water for various needs, including agriculture, drinking purposes, and other daily chores, as well as it is important for the Earth's climate as it reflects the solar radiation coming from the sun and helps regulating the Earth's temperature. Uh, Secondly, if the entire cryosphere melts or entire ice on the Earth's surface melts, it will lead to sea level rise and a lot of land surface will be submerged. So it helps, and also it is important component of the ecosystem and provides life to the wildlife and plants. Uh, where can we find cryosphere on Earth? So the polar regions, including Antarctica, Greenland, Iceland, and high latitude regions like the Scandinavian countries, and high altitude regions like the Himalaya, Andes, and so on. The cryosphere is not distributed evenly over the Earth's surface. As you can see, almost 97% of the Earth's cryosphere or freshwater reserves are located in the polar region. And the third largest portion of freshwater reserve is in Asia, which encompasses the Hindu Kush Himalayan region and provides fresh water to billions of people in the downstream regions. Uh, if we talk about the Indian Himalayan region, in that too as well, the glaciers are not distributed evenly. A large amount of our glaciers are in the northwestern Himalayan region, including J&K, Ladakh, and Himachal Pradesh. Uh, a considerable part after that is in Uttarakhand, and a very small portion of the cryosphere or glaciers are present in the northeast. That is the Brahmaputra and Tista basins. Uh, so what is a glacier? Glacier is basically frozen ice which moves under the force of gravity. So by definition, glacier is a moving body, and if there is no movement in a glacier, in a ice mass, then we do not classify it as a glacier. There are two broad types of glaciers, that is continental glaciers and alpine glaciers. And basically they form when the total snowfall occurring at a particular location is higher than the total melt from that region. So year after year, snow accumulates and eventually turns into ice. And when considerable amount of ice is formed, it starts moving down the slope or depending on the topography under the force of gravity. So that's when a glacier is formed. So these are some typical examples on the left-hand side, you can see a mountain glacier, which is the snout of Gangotri Glacier. On the right-hand side, that's Antarctica ice cap, which is a continental ice cap. And below the photograph is of an ice shelf. An ice shelf is the floating part of the glacier, which is floating over the ocean or sea surface. So basically, when large ice caps, continental ice caps, they move under the force of gravity, sometimes they extend into the oceans or the seas. So that part of the glacier, which is floating on top of the ocean, is known as an ice shelf. So coming to valley type of glaciers, the major uh, what you say, the portions of the glacier include the snout, which is the lowermost part, which is demarcated here, and there is the ablation zone, which is where the ice melts, and there is the accumulation zone where there is more accumulation of snow and formation of ice takes place. An ice fall is where there is a sudden drop in topography, and that forces the ice of the glacier due to its movement to form a stairway kind of a thing, which is known as a ice fall. This is the typical accumulation zone of a glacier in a valley glacier. This picture is from Uttarakhand, Dokriani Glacier, and this is how the ablation zone of a glacier looks.
Assalamualaikum.
This is a debris-covered glacier, typical debris-covered glacier, wherein
Yeah, I can hear you.
am I audible?
Participants,
I'm good.
please
How are you?
mute yourself. Please. Who is Takar Ahmed? Please mute yourself. Sir, you can continue, sir.
Yeah, so this is a typical debris-covered glacier, and the ablation zone of the glacier, wherein the debris is basically derived from the valley walls. As the glacier moves, it erodes the valley walls, and the debris gets accumulated over the glacier surface. And this is a clean glacier. This glacier does not have any debris cover. You can clearly see the entire glacier is totally debris free, and this kind of glaciers, they help in reflecting the solar radiation. So coming to some of the important glacial features, geomorphological features, this is a typical horn. Horn is basically formed when uh, multiple cirques. In fact, I think I forgot to inform you. Yeah. So in this picture, you can see the top portion where the uh, ice is accumulated in between and is surrounded by the valley. That is a typical cirque on top of the picture. If you see on the right hand side top, that is a typical cirque. So when multiple cirques on different sides of a mountain merge, then a horn kind of structure is formed. Here you can see this is one cirque, and there are other cirques on the other sides of the mountain. Erites are basically ridges which are comb-like structure. They are sharp features which divide a basin from the other basin. So if you these are typical erites. On the other side of these erites is a different basin. This is a picture from Nubra Basin, and behind this is the Shyok Basin. So these erites are found basically due to the frost action or the low temperatures and during the night time, and warming up during the daytime. So due to the difference in the temperature, there is erosion, and these kind of erites are formed on top of the ridges. Then again, these are some typical features you can see on the left hand side, top left hand side. These are basically crevasses. This is all ice, and these are crevasses, or you can say gaps which have been formed. And some of these crevasses can go up to the bedrock. So these are actually challenging while working in the field. Cross them and to reach the accumulation zone is a very tricky uh, thing. And so these are some of the difficulties. Even on the right hand side, top right hand side, you can see a typical transverse crevasse, which is up to 10 to 12 meters deep. And on the bottom left, you can see a rock which has striations. These are basically formed because of the uh, movement of the glacier. So in the past, when the glacier was over this rock, due to the movement of the glacier, these striations have been formed. And then on the right hand side, that is a typical rock table which is formed over the glacier surface. Basically, this is part of the debris over the glacier, and due to this debris, there is differential melting on the surrounding part of the ice. So you can see the ice has vanished from the surrounding areas, and this particular rock has insulated the ice exactly below it and formed a rock table. This is a picture of a proglacial lake. So proglacial lakes are basically lakes which are in front of the glacier snout, uh, which I already told you is the lowermost part of the glacier, from where usually the glacier stream or the river starts. So this is a typical proglacial lake which has been formed in front of the glacier. This is a picture from Bhilangna Basin in Uttarakhand only. And then there are periglacial lakes. Periglacial lake is basically on the surrounding of the glacier. So you can see this is a typical debris covered glacier, and this is the moraine. And adjacent to it is a lake. So this is a periglacial lake as it is adjacent to the glacier. So coming to climate change, we all know there is anthropogenic emission of greenhouse gases, and CO2 is one of the primary greenhouse gases. So, and temperatures have risen from about 1.2 to 1.5 degrees, depending on the region, in the past 100 years. Sea level rise is a major concern, and many of the island nations are already uh, facing this issue. So, why is climate change important to the cryosphere or the Himalayan region? So, since already I told you that Hindu Kush Himalaya or the Indian Himalaya are known as the third pole or the water towers of Asia. They are the source of 14 major rivers in the region, which on which a large population is dependent. So, if the cryosphere melts or disappears or even reduces considerably, we'll have consequences on water availability, and as well as it will have a negative feedback, since the cryosphere, the snow cover, the glaciers, they reflect back the solar radiation. If the snow cover and the glaciers reduce, they will provide a negative feedback and in turn increase the rate of warming. So that's why this we all know. Most of you may have seen that how the atmospheric carbon dioxide levels have changed over. This is for over 8,000 years till present, and you can see in the latest period. the greenhouse gases have increased exponentially. In fact, exponentially is a very mild term. You can see it's a very drastic increase, and we need to look into that. So another important factor is black carbon. So black carbon basically absorbs solar radiation and creates warming. And when this deposits over the cryosphere, over the snow surface or the glacier surface, it reduces its albedo and leads to more warming and faster melting of the ice. And uh, these black carbons are going to increase in the near future as uh, part of development, increasing infrastructure, road connectivity, and things like that. So the black carbon emissions in the mountain regions are going to increase, and this is a major concern as far as cryosphere or glaciologists are concerned. So you can see this is basically cumulative mass balance over Greenland and Antarctica, that is the north and south poles. And you can see after 2000 there is a drastic decrease. Basically, mass balance is the uh, uh, balance between the accumulation and the melting from the glacier. And this particular graph depicts clearly that after 2000, there is drastic decrease in the mass balance, or rather drastic melting from the glaciers in Antarctica and the Greenland. Similarly, these are some 12 reference glaciers uh, from the Arctic region in Canada and the Scandinavian countries. Here also we can see after the 1980s or 1990s, there is a drastic decrease in the mass balance of these glaciers, and up to the order of minus 30 meters of water equivalent every year. Uh, this again is for mountain glaciers given by the World Glacier Monitoring Service, WGMS. And you can see again the extent of melting every year is about minus 30 meters of water equivalent every year. That is, and can see initially there was a dip in the melting during the 60s and the 70s, but then again after 1990 there is a drastic increase in the rate of melting and a negative mass balance is observed. This is a similar graph for glaciers in the US for a period of 1952 to 2023. These are some visual changes. You can see the entire area has lost its snow and ice cover. This is the upper picture is for 1933 and the lower picture is for 1912. This is a glacier from Italy in the Alps. Similarly, in the Indian Himalayan region, this is a picture for Dokrani Glacier, 1995, 2013, and 2017. You can clearly see in this picture, the surface of the glacier is above, whereas the surface has lowered in 2013, and it has further deteriorated in 2017 with longitudinal crevasse running through the length of the glacier. So these are alarming signs for us, and we need to really look into global warming and climate change and reduce our greenhouse gas emissions. So as far as glacier monitoring in the Indian Himalayan region is concerned, a total of about 19 glaciers have been studied so far out of almost 10,000 glaciers. Uh, that is partly because of lack of infrastructure and logistics, and partly because of the harsh climatic conditions and accessibility in the Himalayan region. So out of those 19, these are the 19 glaciers that have been monitored, and these are the periods for which they have been monitored. So you can see that Dokrani Glacier is one of the longest studied glaciers. It has been studied since 1992, and the studies are continued at present, in fact. And the second longest data availability is for Gangotri Glacier. And even this study is continuing till now. These are typical setup of our camps and observatories. You can see this is a typical setup of camp in tents, whereas in the lower picture you can see we have huts. So if we have a hut at the glacier camp, that makes our life easier, and it makes it easier to monitor the glacier. And on the right hand side are the meteorological observatories. On the top picture, you can see a typical manual observatory, which is recommended by the India Meteorological Department. And in the bottom side, you can see a conventional meteorological observatory, as well as a automatic weather station. So this is a automatic weather station, which I am talking about. And so basically, the automatic weather station has different sensors. The conventional observatory has different thermometers, including dry bulb, wet bulb, minimum, maximum thermometers. Then we have thermographs, hygrographs for hourly observations. And then we have sunshine recorder to record the uh, sunshine hours we get in a particular day. And then we have anemometers and wind vane for wind speed and wind direction, and as well as pan evaporimeter to uh, observe the evaporation occurring at that place. So typically we take observations at 8:30 and 5:30 in the evening, 8:30 in the morning and 5:30 in the evening, which has been subscribed by the IMD, which are the standard timings for observations from the conventional observatory or the manual observatory. And then automatic weather stations, we have different sensors at different altitudes. At 2 meters, we have the air temperature and relative humidity sensor, along with the barometric pressure. Then above that, we have the solar radiation sensors, and at the top, we have the wind sensors. So these weather stations can log data at different scales, at every minute, every hour, and at daily scale. So since the advent of weather stations, we can generate high resolution data sets without the manual labor which is required with the conventional observatories. However, sometimes these observatories malfunction, these weather stations malfunction. That is the reason you can see here we have 3 weather stations within the same basin. So if one of the observatory does not work, we can rely on the other 2 observatories to fill the data gaps for the third station. So how do we do this data gap filling? Basically, we have done simple regression models. We have prepared am I audible? There was some network issue,
Yes,
I guess.
yes, yes. You're audible, sir.
Okay. Yeah, thank you. So this is basically a depiction of the standard data on daily and monthly basis. The line graphs are the daily data for minimum, maximum, and mean temperature. And the bar plots are basically monthly temperatures, mean, minimum, and maximum. So, and as well as the lower half of the graph depicts the atmospheric pressure, the variability in the atmospheric pressure on daily as well as monthly basis. Uh, we also use satellite data. These days, reanalysis data is prevalent. Some of you might have used as well. However, these satellite data have certain biases and they need to be corrected. So what we do is we calculate the biases, the percent biases, the RMSE and NSE for this data using our observed data. And this is basically a regression, again, regression analysis on daily and monthly basis. And based on the regression analysis, we correct the bias. And on the right hand side, you can see these are the these are the corrected ERA5 data in the blue. As I said, snow is an integral part of the cryosphere. And for snow cover studies, we use satellite data from different sources. And this is basically a depiction of monthly snow cover. In this, June, July, and August period is missing. Otherwise, from January, February, April, May, September, October, November, December is available. Basically, during the monsoon season, there is a lot of cloud cover. So it is very difficult to get a cloud-free image during that period. However, using these images, May and September, we can interpolate how the snow cover is changing. And basically, this is also important for modeling studies of the hydrological modeling, how much water is coming from different components if we want to analyze. So this snow cover is very important in that aspect. And you can see the minimum snow cover is in the month of September, that is at the end of the monsoon season. And then again, you see there is certain addition to the snow cover in November, and then again in December, the entire basin gets covered by snow. So, and these are the topographical variations of snow cover based on the elevation, the aspect, the direction in which it occurs, and on the slope of the mountain. So you can clearly see that there is large variation in basically these are the coefficient of variations, and there is large variations on the lower slopes and the higher slopes. So higher slopes, the variation is basically because of the fact that a large number of avalanches takes place on higher slopes. So the snow is displaced from higher slopes to lower slopes, and that's why there is a larger variation in the higher slopes. Whereas in the lower slopes, it is due to the rapid melting of the snow. Because these lower slopes are usually at lower altitudes, so that's why the snow gets melted rapidly. Similarly, you can see for elevation, the variation is higher in the lower elevation zones, because the higher elevation zones are mostly in negative temperature, and the snow persists throughout the year. And another important factor is for having multiple observatories in a basin is to understand the temperature lapse rates. As we all know, the environmental lapse rate or the adiabatic lapse rate is 6.5 degrees per kilometer. However, based on our data, we found out that the temperature lapse rates vary according to the season in the mountain regions, and it varies from about 4.5 degrees centigrades per kilometer to up to 7 degrees centigrades per kilometer. So this is a large variation, and considering a simple value of 6.5, universal value of 6.5 does not always provide the correct simulations or the correct information for policymakers uh, in the downstream regions. So this is the top left corner is the temperature lapse rate, and below that is the isotherms. Isotherms are basically imaginary lines which connect the uh, areas or elevations with the same temperature or with the same thermal gradient. So you can see the isotherms we have prepared for 0 degree, 1 degree, and 2 degree. These isotherms basically again vary according to the season. As in the summer season, the temperatures are higher, so these 0 degree isotherms reach at higher altitudes. Whereas during winters, they are at lower altitudes. Again, the importance of this is if we consider that snow and glaciers start melting at 2 degrees centigrades. So what will be the contributing area of a particular basin which contributes to the meltwater generation in that particular basin? So for that, if we consider 2 degrees, we'll get a larger, lesser area. If we consider 0 degrees as the melting point, then we get a larger area uh, of contribution from a particular basin. Uh, in this particular thing, you can clearly see the 0 degree centigrade and 2 degree centigrade isotherms are at 5,400 and 5,100 meters. So there is a difference of about 300 meters. So it is very important to consider while doing hydrological modeling for downstream regions, what threshold temperature you are taking for the melting of snow and ice. Then these are the typical hydrological observatories in the Himalayan region. This is an example from Dokrani Glacier. You can see in 1995 and 2011, the same hydrological observatory has been operated with certain modifications, obviously. And this is a automatic water level recorder, which was of mechanical type, installed in 1995. And the one on the right hand side is a digital water level recorder. These both water level recorders are a contact type, that is a float is within this well, and this well is located here. And when uh, water comes into the well, the water level increases or decreases, the float goes up or down, and that's how the recordings are taken place. However, recently in 2019, we have installed a non-contact water level recorder, which is on the principle of radar. So it basically sends beams below it and records the water level. Similarly, there are other methods uh, like salt dilution method and diatresia method to uh, observe the discharge of a particular river. Although these are not used very much due to the environmental factors, and we mainly use area velocity method, wherein a fixed cross section of the river uh, is monitored for the water levels, and typical rating curves are formed, which is a relationship between the stage, that is the water level we have recorded, and the discharge passing through at that particular stage. Uh, so we take cross-sectional areas every time, and at intervals, and based on that, calculate the discharge of that particular day using area velocity method, that is area into the velocity of the water and the water level. Based on the water level, we find the area under the curve, and we multiply it with velocity to find the discharge at a particular day and time of the year. And based on that, these stage discharge relationships, which are on the left hand side, are formed. And once these stage discharge relationships are formed, you can only take the stage reading and calculate the discharge for a particular day or particular time of the day. Then based on hourly observations of discharge, uh, we calculate the day and night variations or the diurnal variations in discharge. Here you can, this is a typical example from Dunagiri Glacier, where you can see the nighttime discharge is higher than the daytime discharge. So you must be confused why this is happening. Although the nighttime temperatures are lower than the daytime temperatures, so how come the discharge at nighttime is higher? So the basic concept behind this is that the glaciers usually store water within them as supraglacial lakes or in the subglacial channels, which are formed beneath the glacier surface, that is between the bedrock and the glacier. So and this water is released during the night time, or it is because of the fact that melting takes place from different regions of the glacier, and it takes time to reach the discharge site or the observation site, uh, which is the lag time for the meltwater to reach a particular observatory. So that could be the other reason for higher nighttime discharge. So again, why hydrometeorological observations are important in combination? So we can create multivariate regression equations using the meteorological and hydrological observatories to find out the discharge. So basically, in this the equations, the Q is the discharge, T is the temperature, different temperatures, mean, maximum, and minimum temperatures. R is the rainfall, and WD and WS are the wind direction and wind speed. So, and some of the places you can see we get quite high correlations, and these are then utilized for simulating or estimating the discharge at different times and different months of the year. So we also carry out flow dependability analysis, how much discharge we'll get at a particular time. So this is basically a probability analysis. For different months you can see, and we for different uh, quantities of discharge, 50% dependability, 75% dependability, 90% dependability. So basically 50% discharge, which is about 6.6 meter cube per second. So 50% of the time in the month of June, we'll get uh, uh, 6.6 meter cube of discharge. Whereas if we want 90% dependability, we'll get only 6 meter cube per second discharge during the month of June. Similarly for different months. So this is basically important for the hydropower power stations and irrigation systems which are being developed in the downstream regions to understand how much water they will receive and how much electricity they can generate, or how much water they can divert through canals for irrigation. So this is the basic purpose of flow dependability analysis. Similarly, suspended sediment is an important factor. Here you can see suspended sediment exponentially increases with temperature. That is, if during the summer months when the temperature is high, the sediment concentration is also high in the rivers, in the Himalayan rivers. So Why is this important? Again, this is important from the hydropower perspective. They need to know how much sediment is going to come, how it is going to affect the reservoir, and it also affects the turbines and the electricity generation. Basically, these sediments are so fine that when they hit the turbines, they erode the turbines, which and sometimes these hydropower stations during the summer period have to stop production of electricity due to high sediment load. And this temperature is important because with climate change, the temperatures are rising, and if in the future considerable temperature increases are there, the this sediment load and concentration is going to increase. Then there are another important factor is the water availability using models. So these are some studies in different basins in Spiti, in Satluj, and in Dingad Basin in Uttarakhand. Spiti and Satluj basins are in Himachal Pradesh, and here you can see the models have predicted up to 6 to 12% increase in the water availability or discharge from glaciers and snow and glaciers in this region. Whereas in Satluj Basin, it is a negative impact of 6%. And again, in Uttarakhand, it is a plus 28%, which is a very high percentage. Um, this is primarily because of the fact that Spiti Basin has uh, large glaciers which are less affected by the uh, ongoing climate warming, whereas in Satluj Basin, the glaciated area is higher, but it is dominated by smaller glaciers. So, therefore, indicating a negative trend in runoff at 2 degrees centigrades. A 2-degree rise in global temperature will lead to 6% decrease in runoff from Satluj Basin. And similarly, in Uttarakhand, this Dokrani Glacier is a large glacier, and it is a clean glacier, does not have that much of debris cover. Therefore, it reflects most of the radiation, and the changes in temperature will going to increase the discharge from this glacier. Again, there is heterogeneity. This is a study which we did using stable isotopes of water, that is oxygen and hydrogen isotopes. And we can see that they quite well reflect the changes in the discharge which is occurring from the glacier. And another important factor which we found was that the debris cover of the glacier that also modifies the isotopic composition of these glaciers. Coming to the glacier lakes, uh, glacial lake inventories have been formed for different states. In Uttarakhand, there are 1,260 glacial lakes, out of which about 20 glacial lakes have been identified as potentially dangerous glacial lakes. And for Himachal Pradesh, there are 958 glacial lakes, and again, about uh, uh, 15 or 20 glacial lakes have been identified as potentially dangerous glacial lakes. Um, Dangerous glacial lakes in the sense that they can cause glacial lake outburst floods, commonly known as GLOFs, which you might have heard of. In Kedarnath in 2013, a typical GLOF event took place where periglacial lake dammed by the lateral moraine of the glacier breached and caused devastation in the downstream. Uh, these are some pictures and analysis which we did. This is basically Gaurikund, and this particular place is Rambada. If any of you have visited Kedarnath, I'm not sure. Uh, so this was Gaurikund before the disaster, and this was after the disaster. You can clearly see uh, there was total destruction and nothing was left. Again, this is again a extreme event. A flood took place in 2017 from Gangotri Glacier, and it totally changed the geomorphology of the region. And in the below panel, you can see Dokrani Glacier, the site which I had shown earlier as well, the hydrological monitoring site. It was totally devastated after a event in, this was in 2016, flood, heavy rainfall took place and which caused flooding, and you can see the total devastation of the discharge site. So we had to, in fact, relocate this observatory after a period of about 20 years of observations. Um, this is the event which I was talking about in Gangotri Glacier in 2017. You can see the snout region is totally changed, and this is the sediment which came with this event. A large amount, you can see almost more than double the maximum amount of sediment which is observed was received on that particular day. And these are the remote sensing based analysis. Uh, why this event took place? Basically, this is Gangotri Glacier, this is Meru Glacier, and the stream from Meru Glacier was flowing through here. And since this glacier retreated, the main trunk glacier retreated, it left the lateral moraine of the glacier weakened, and due to heavy rainfall uh, and seepage through the moraine, this moraine failed. So basically, this part of the moraine failed, and it caused deposition in the downstream region and erosion from this region. So this is the erosion part. That is where the moraine failed, and this is where the sediment was deposited. And again, in Chamoli, 2021, a massive ice rock avalanche took place. Basically, a large part of hanging glacier from this region, it detached and fell down, and which caused havoc in the downstream. This is the glacial lake which was found due to the damming from this fall at the confluence of Rishiganga and Ronti stream. And this is was the site of the hydropower project which was in the downstream at Rishiganga. And there was a bridge here which was damaged. It was a permanent bridge which got completely damaged. And this particular site is the Tapovan NTPC hydropower plant, which was the primary focus in the news channels when this event took place, and a large number of people lost their lives at this location. Yeah, thank you.
Participants, anyone have questions? They can raise their hands so I allow them to speak. Shireen ma'am, do you want to ask question? You can ask.
Please feel free to ask anything, even a general question is fine, because I know this topic is new for most of you, and a lot of information to take in a small period. Any of the participants been to a glacier?
Sangram sir, you can ask question.
Good evening, sir.
Yeah, good evening.
Sir, one of side says glaciers temperature is minus plus.
During the summer period, at the glacier surface, the temperatures are in positive. It is only above a particular altitude, say 5,000 meters, that temperatures remain negative throughout the year. That is what I had shown, the 0 degree isotherm. That was depicting the temperatures. So basically, the 0 degree isotherm is at 5,400 meters. So above that, the temperatures are always negative. However, below that, temperatures are positive during summers. So glaciers are glaciers in Indian Himalaya range from 3,800 meters to 6,000, 7,000 meters. So the ablation part of the glacier is has positive temperature. That's why the melting of glaciers takes place, and of snow and glaciers, in fact, takes place, and rivers, we get water in the rivers.
Okay, sir.
Excuse
I
me,
hope
sir. I have one
Sangram. Yeah,
question.
Kalyani ma'am, you can.
Yes,
Sir,
yes,
I
ma'am.
just wanted to ask how many glaciers are there in Uttarakhand? Means not exactly, but
Ma'am, around
could you give me?
960 glaciers in Uttarakhand.
Okay, okay,
Ni-
okay.
960, total of about 10,000 glaciers in entire Indian Himalaya region.
Okay.
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 Yeah.
Thank you. Thank you very much, sir.
Any questions from anyone? Shireen ma'am, you can ask question.
Hello, ma'am. Hello, Anjali, madam.
Hi, yes.
Yes, I wanted to ask one question. Can I ask?
Yeah,
Yes,
sure,
yes,
ma'am.
sure, ma'am.
Sir, I just wanted to ask, what are the factors that matters in the calculating mass and volume of glacier? Means, can we
So,
means
ma'am,
different?
there are different methods which we use to estimate the mass balance of a glacier. One is based on satellite observations. So, basically, we use a digital elevation model, DEM, of different time periods, say one from 2015 and one from 2020. And so the difference in the elevation uh, provides us how much ice mass has been lost from that particular glacier. So that is one way. And the other method is in the field. So we
Okay.
install ablation and accumulation stakes on the glacier surface. So they are basically bamboo sticks with the markings on it. So we put them into the glacier surface, and then every
Hello, sir. Hello,
Uh,
hello. I
sir,
think sir
you are
is.
not audible.
Sir, you are not audible, sir.
yeah,
Yes, yes,
Yeah,
sir is
now
okay.
back
audible.
now. Huh.
Yeah.
Yeah. So in the accumulation zone, we put accumulation stakes. In the ablation zone, we put ablation stakes to monitor how much accumulation or melting of the glacier surface is taking place. And then using simple interpolation and uh, other graphical methods, we calculate the entire mass balance of the glacier.
Okay, sir. And where can we get the accurate data set if we want to do the means research or to study for the glacier recording mass and volume? Can we get the accurate
Uh,
data set?
Ma'am, that data set is not available freely anywhere because
Oh,
different organizations are working in the field and collecting data. So some of the published data is available definitely, but that raw data set you won't be able to get.
okay, 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 sir. Thank you.
But
Thank you very much.
satellite data set is available, freely available.
Okay, okay, sir.
Okay, another
Thank you very
question from Ved sir, Ved, Nikki Ved. You can ask now.
Good evening, sir. Am I audible?
Yeah, you are
Yes,
audible.
you can carry on.
Yeah. Thank you, sir. The session was very knowledgeable. Actually, I just wanted to ask a very common question. As we know,
Yeah.
Ganga will never get dry. We know it very well because of the glaciers get melt in the summer season. As due to the global warming, the glaciers are getting melt in the in the winter season also due to the global warming. What will be happening in the upcoming time? I want to know about that thing. Is any study done over that thing?
Yeah, there are certain projections which have been made, global projections that have been made, although there are no, you can say, dedicated projections for the Himalayan region done by anyone, but the global projections are there, and there is a possibility that about 60 to 70% of our glaciers will melt by the year 2100. So only 30% would remain.
Okay, thank you so much, sir. Thank you.
Sir, I
Sir,
have
I
one
have
question.
question one that can you explain the software method to calculate mass and volume? Is there any another method which is we can use?
Ma'am, the simplest method is using the digital elevation model, that is satellite-based data, because field monitoring is very uh, what you say, difficult due
Okay.
to the terrain and climate, as well as it requires a large amount of logistics and dedication, and you need accessibility to the glacier as well. So that is difficult. So I would suggest you can do, if anyone wants to do, uh, simple digital elevation model for different periods you can take and do the difference of that using ArcGIS or whatever software you are using, and
Oh,
you can find.
okay. Do you mean to say that DEM model we need to see that which month we should select, and according to that DEM on that month we should get it?
Yeah, ma'am. Usually what we do is, for the Himalayan region, end of October is the period which we target, because that
Okay.
is when the temperatures uh, go into negative, and relatively the melting reduces.
Okay, sir.
So
Thank you.
on
Huh.
basis
Yeah, yeah,
to
carry
do,
on. Huh, sorry.
if on annual basis you want to do, every year October period you should target.
Okay, sir.
So there is
Thank you
one
very
question
much, sir.
from the participant.
Yeah.
Explain the role of satellite in glaciers outbreak.
Uh, Glacial lake outburst flood, or I think it must be that only. So satellite data always is, we get after any event takes place. We cannot get that data in real time. So uh, role of satellite data for monitoring hazards in Himalayan region is only after the event. We can only tell that this and this thing happened, or this much displacement took place. We cannot use satellite data for real-time monitoring. For real-time monitoring and early warnings, you need to have monitoring systems on the ground itself, which send you data in real time through either mobile network or through satellite. So that's where satellite comes in.
Okay, sir. Thank you.
Anjali madam. Hello.
Yes,
Hello.
Kalyani ma'am. You can ask
Yes.
question. You're audible.
Okay. Okay. Yes. 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 Thank you, ma'am. So, sir, I just wanted to ask one question again. That what are the research that are rarely done on the glaciers,
So, ma'am,
so that one can understand that he can do the research again on that topic.
so, ma'am, typically what we do is hydrometeorology as well as mass balance studies. The upcoming field in glaciology is use of uh, seismic data, that is seismology, seismometers, to identify glacier movements and different hazards like avalanches or debris flows or different things. That is one area. Another upcoming area in glaciology is the study of permafrost. Permafrost is
Okay.
basically, ma'am, frozen ground. So that's those studies have not been done so far in the Indian Himalayan
Okay.
region.
Okay. Okay, sir. Thank you. Thank you, sir. Thank you, sir.
Any questions from participants? So one question I think.
Parshuram. Yeah, Parshuram sir, you can ask question.
Yeah, sure.
Yes, sir, you're audible. You can ask. Parshuram sir.
Yes, Parshuram sir, am I audible?
Yes, you are audible. Please go ahead.
Okay, any questions from participants? Okay, I think there is no questions from the participants. Let's move to the next session, that is a vote of thanks. So on behalf of, yes, Anjali madam, so can you conclude that this session?
Sir, you continue just.
Yeah. So on behalf of Bharati Vidyapeeth College of Engineering for Women, Pune, I extend my heartfelt gratitude to our esteemed speaker, Dr. Akshay Verma sir, for delivering such thoughtful, provoking, and enriching sessions. Your expertise and insight have been truly valuable to all of us. I also thank all the participants for their active engagement and enthusiasm throughout the session. Thank you, sir.
Thank you so much.
Yeah.
Kiran sir,
Yes, ma'am.
Kuldeep sir is there
Okay.
in the meeting.
So all the participants use the same link for that the next session. Immediately next section will be the start. Hello, Kuldeep sir, am I audible?
Yes, yes.
Yes. Okay. So can you start that session, sir, immediately? Yeah, wait for.
Yeah, I can. Shall I
Sir,
share
sir. Sir, can you give the introduction of sir?
Yeah,
myself?
I will give the introduction, sir. Okay.
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 Shall I
So
share
good
my
evening.
screen first?
Yes, sir.
Wait,
Sir,
wait.
Kuldeep sir, wait for a introduction by Kiran sir, and then you can share your screen.
Okay, no worries.
Yeah,
Okay.
thank
Okay.
you.
Yeah. So good evening, everyone. A warm welcome to the Faculty Development Program, which are organized by Bharati Vidyapeeth College of Engineering for Women, Pune, in collaboration with the National Institute of Hydrology, Roorkee. We are excited to have you here for this enriching experience. Now it is my privilege to introduce our esteemed speaker for this session, Dr. Kuldeep Sharma sir. Dr. Kuldeep Sharma sir is a scientist C at the National Institute of Hydrology, Roorkee, since 2023. His research focuses on generating high-resolution climate information using dynamic downscaling and the WRF model, particularly in the Indian Himalayan regions, addressing the climate change impact on environmental and hydrological process. Dr. Kuldeep Sharma sir previously worked at the Center for Climate Research, Singapore, developing a convective ensemble prediction system for Southeast Asia. Sir has also worked at the National Center for Medium Range Weather Forecasting for 10 years, specializing in regional modeling, weather forecasting, and model evaluations. Dr. Sharma sir holds an MSc in physics from Aligarh Muslim University and MTech in atmospheric science from Pune University and PhD from Banaras Hindu University in 2018. He has published 20 research papers, 3 book chapters, and 4 internal reports for National Center for Medium Range Weather Forecasting. Sir has with over 14 years of experience in weather modeling and climate research. Dr. Kuldeep Sharma continue to make valuable contribution to the field of climate science. We have honored to have with us Dr. Kuldeep Sharma sir and look forward to your valuable insight. Welcome sir and thank you sir for this session. Over to you sir.
First of all, I would like to thank you, Dr. Kiran, for nice introduction, which I was also not aware how much work has been done over the period of time. So thank you very much for your kind words. With this,
You,
I would like
yeah.
to share my screen.
Yeah, you can share your screen, sir.
Is it visible?
Yes, sir, it is visible.
Now screen is visible?
So there is a lag, but your team screen is visible now.
Now my screen, now are you able to see the slides?
Not
No,
yet.
sir. No. No, sir. Your slides are not visible.
Okay.
Sir, try to share it again.
Now?
Yes, it is visible now. Yes.
Now my slides are also visible?
Yes, sir.
Now?
Yes,
Yes,
sir.
sir. It's visible.
Okay, fine,
Yes,
fine,
sir, it
fine.
is visible.
Yeah. So, as mentioned that today's topic is the cutting edge development in weather and climate modeling. So, as you all aware that weather, how important the weather is for all of us in different aspects, as well as climate. So, there are lot of things happening nowadays in weather and climate modeling, and it is not because of the research and development has gone so ahead. It is because of there are lot many things which is keep on going on in terms of development in the technology. So what we understand in terms of weather and climate. So and to be honest with you, then why it is required to forecast weather. First of all, every one of us, whenever we are traveling to one place to another, immediately we look at the temperature of that place, where are we going. So why it is required? Because we have to plan accordingly. So if we have a proper information of weather ahead in time, then we can plan our visit, we can plan our so much of activities ahead in time. So there are different aspects of weather forecast. So I will first of all in my talk I will take what is weather, what is the advancement in the weather modeling. Then later down the line we will see the climate modeling things. So as we all know, the weather affects nearly everybody and every day. And why it is required? Because it helps you to save lives. It helps you to plan the things in such a way so that you can minimize the risk. You can minimize the risk by reducing the property damage. And people, the general public is also aware what to expect from weather, what is going to happen in future, so that we can plan our activities accordingly, in terms of weather information ahead in time we know. So that is what I was saying, that decision making is one of the most important things in everybody's life. In many sense, you will see all of us are working in some of the organization, we are studying something. So one thing which always encounter with is decisions. So if you take decision on time, then you can plan your things in that way. If your decision may go right or wrong, but still you have to plan things based on your decisions. So decision making is important. So that is the same case in terms of weather. So if you will look at what kind of things are being forecasted, one is the most important thing which is important in terms of weather forecasting is the monsoon. In terms of the rainfall during the monsoon season of JJAS, rain. This is, and next is the extreme weather events such as cyclones, extreme weather events in terms of fog forecasting. Apart from that, there are lot of application of weather forecasting. Monsoon, cyclone and fog, these are the direct atmospheric phenomena which is important to forecast. There are different application of weather forecasting which is being applied, and in different sectors. The major sectors are, all of you are aware in nowadays, is the air quality. In Delhi, during this winter time, October November time, everybody might have seen in the newspaper that there are lots of smoke activities are going on. So how do you forecast those things? If you couple your weather model with air quality models, then you can have a proper information about air quality forecasting, how the air quality is being driven. The major driving force in terms of air quality is the weather parameters. So winds are most important in terms of air quality forecasting. Apart from that, local information, local emission, how the local emissions are driven. Local emission are driven basically with the information of atmospheric parameters. So next thing comes in the hydrological modeling is flood. So if you have the proper information of correct information of rainfall ahead in time, that this much amount of rainfall is going to happen, then you can calculate how much flood is going to happen in that region. So again, the importance of weather forecasting in different application is you can see that air quality, even the flood, even in the avalanche information. So if you have well in advance the snow melt runoff modeling, all those things, if you want to do, so if you want to look for the cloud burst event, then you must have weather information ahead in time. So ahead in time means, depending up, if we are talking about weather forecast, then we are dealing with at least what is going to happen in next 10 days. So accurate. So like this is different application of weather for information is wind energy, and now solar energy. So these are the renewable another emerging area where weather information is critical to know in advance. So this is the application of weather forecasting. If you have proper weather information ahead in time, so these things can be targeted in terms of application forecasting, and direct implications in terms of monsoon, cyclone and fog, and extreme weather events, severe weather events, which is like in northeast thunderstorm is one of the prominent phenomena even in the pre-monsoon season, pre-monsoon thunderstorm activity in the northeast region. So that is very localized phenomena, but if you have proper weather information, if you have a strong observation network, then you have a better quality in your forecast. So what are the ranges of weather forecasting? How we, what kind of things we do say this is nowcasting, it is medium range forecasting, it is extended range forecasting. You might have heard about the long range forecasting as well. So if you are talking about the very short range forecasting up to 12 hours, then this is up to 12 hours. If you will say within 6 hours, that is called as nowcasting. Short range forecasting beyond 12 hours to 3 days, up to 72 hours. If you are forecasting that this comes under IMD's nomenclature, is the short range weather forecasting. If you go for a medium range forecasting, that goes beyond 3 days but restricted up to 10 days. So 3 to 10 days forecast comes under a medium range forecast. And if you go for the extended range weather forecasting, so beyond 10 days to 30 days, and long range forecasting beyond 30 days to 2 years. So remember, so this is the ranges of weather forecasting, but you have, and these forecast has to be applied for different applications. It is not simply, there are lot many agencies which I have encountered with, they are using climate data for dam operations in hydrology. Since I do come from National Institute of Hydrology, but that is not justified. So if you are doing the reservoir operations, dam operations, in that case, you do not require the climate data. You have to look for the weather forecast that is beyond 10, up to 3 days, up to 72 hours. If you will look for the climate information for such type of thing, so you have to apply your brain. You have to understand where this weather forecast has to apply in which kind of problem. So that depends upon the problem which you are targeting to sort out in terms of application of weather forecasting. So how a weather forecasting happens? There are different ways. Earlier it used to be a synoptic method. So based on the balloon observation and all those things, they try to forecast weather, but that forecast was subjective and they may go wrong. So the latest development has been in terms of numerical weather prediction modeling. So nowadays you people might have heard that there is a lot of improvement in the weather forecasting in terms of cyclone forecasting. Proper weather information is being released. That all credit goes to the numerical weather prediction, which is a very objective method to provide a weather forecast. And what are those numerical weather prediction models? The numerical weather prediction models are those tools which are being utilized objectively to forecast weather, and this is a mathematical representation, and these are the set of computer programs. This is designed to simulate a real-time phenomena, that is in case of weather, real-time phenomena like tropical cyclones, like monsoon depressions during the monsoon season of June, July, and August, September, which originate over Bay of Bengal, generally in these monsoon depressions, and move towards westward. So those monsoon depression, tropical cyclones, if you want to forecast those events, so we are utilizing these numerical models, and these numerical models are again set of computer programs which are written in Fortran and C, and a combination of different languages. So those programs are being solved using a very high performance computing systems, and and these programs, and one thing, if you are giving a very good forecast but at a later time, so there is no point of releasing such type of forecast. So your forecast should be well before time, so that actions can be taken based on the forecast information. So for, if you want to run your models well before time, so how can you run? So you need high performance computing system with a very high capacity, so that your program at a global model or a regional model can be run well before time. So if you are running and same times what happens, then your forecast forecast will never be accurate as you are expecting. So you have to understand this is the limitation, this is the uncertainty in the forecast. So you have to utilize your weather forecasting skill to release that forecast and how it has to be interpreted as well. So equations are based on laws of physics, and these are integrated forward in time and space to simulate changes in the atmosphere. So if at certain point of time you have, this is the weather conditions, what will be the weather conditions in next 3 days? So what you have to do, you have to do integrate forward in time. How the integration method works? So this is the component component of a numerical weather prediction model. So what you do, you first develop the initial condition, and then once you have initial condition, you utilize the governing equations, you put those governing equations, and you apply the numerical methods to solve the problems. When you are running a regional model, then you require boundary conditions as well. There are two types of numerical weather prediction model. One is global model, when you are targeting whole globe to run your global model, to release the forecast for whole globe. In that case, you don't require boundary forcing. Boundary forcing means what? At your edges, you must be knowing that your it's an initial value problem, and its atmosphere is non-linear. So after certain point of time, you will your model will reach to, will start going to non-linearity. So if you are running the regional model, in those cases you have to provide the proper boundary conditions so that to bring to the natural to linearize your model. So, and apart from, there are lots of physical processes in the atmosphere like boundary layer processes, convective scale processes, cloud processes. So you have to simulate all those processes in your model so that you will represent the atmosphere in the best possible way. But there is always a limitation in representing the atmosphere. So there are certain assumptions to be considered to run an atmospheric model that comes under a physical process representation that I will come into my later slides. Finally, once your model has been run, you will get model output. So based on your model output, you will interpret the weather forecast. What is going to happen in future, in next 10 days, in next 5 days, depending upon your forecast length. So that is what I told. Numerical weather prediction is an initial value prediction. If you have exact initial conditions, if you have represented the atmosphere exactly, then you have the best forecast. But is it possible to represent the initial condition exactly as available in the atmosphere anytime? No. You can never represent, you can never have the best initial condition, because initial condition, how do you develop initial condition, is the collection of observation. There are different kind of observations you utilize to develop the initial condition. How you develop the initial condition? Initial conditions are developed using a method called as data assimilation. Data assimilation, what does it do? It is a process which combines the with with the short range forecast. Short range forecast, what do we call, is a first guess. How do you, suppose you want to run your forecast at 0 UTC. 0 UTC means in Indian time it is called as 5:30 in the morning. Then you must be having your 6-hour forecast as a first guess, or 3-hour forecast as a first guess, depending upon your computational power. If you are considering 3-hour forecast as a first guess, so you have a short forecast from 21 UTC. So 3 2:30 2:30 3 hours before the 5:30. So 2:30 you will release a forecast, that is the first guess. Then you have base. In that you have to assimilate the correct observation, that is called the data assimilation methods. So there are different data assimilation methods available. So it starts from the Crestman methods. Now it is the 4D hybrid ensemble, then 3D var assimilation, 3D variational method, then 4D var, then hybrid 4D var, then hybrid ensemble 4D var. So these are the name of different data assimilation methods are being utilized. The latest, the coupled hybrid ensemble data assimilation method. So this is the coupling of atmospheric as well as the oceanic data to represent the best initial condition of the atmosphere. And from there, they are running the model next ahead in time for 10 days. So this is how the initial conditions can be seen up. So you have a different sources of data, buoy data, radio sound observations, aircraft observations, and the most important observations are the satellites. Though the time where the satellite data has come in immensely into the observation into the data assimilation techniques, so that has improved the weather forecasting quite a lot by a large margin. I will see, I will show you the data in the next slide. So how these data sets, so this all satellite data, geostationary polar orbit satellite, ocean data set, weather ships, automatic weather station, all these data sets are being assimilated, bringing at one point, and then you are adjusting with the first guess, so that initial condition in that case is called as the analysis. So you have analysis means you have assimilate all the available observation at that time and develop a initial condition. That method is called as data assimilation, through which you are assimilating your data. That method is called, and the data initial condition which is developed, that is called as analysis file. So once you have analysis, then from there you have to integrate your forecast forward in time for next 10 days or 5 days or 3 days, whatever your computational capability and your requirement. So this is how the instrument, how the satellite data has been emerged over the period of time. So you can see then 1982 INSAT 1A. Now we have that ocean set, and even this latest information, there are other satellite data has also been incorporated. So the journey from the satellite data has been started. So this much data set, and you can see, so not only Indian satellites but all other satellites are also being utilized to develop the initial condition at a global scale. So this is the, and different satellite has different paths. So merging of all those satellite information like INSAT 3D, GOES 16, Himawari, Meteosat, NOAA, Aqua, GPM, all those data set has to be merged, has to be assimilated, and make one initial condition that is being utilized for running the model ahead in time. So this is how the year-wise volume of data. This slides cuts I have taken from NCMRWF, and this is the national agency who is running the model every day twice. At one is 0 UTC morning 5:30, another is 12 evening 5:30, that is 12 UTC. So you can see after 2015, after after 2015, you can see the increase in the volume of data which is going on into the model. This is how the data set is being received. This is the observation data which is received. One is through GTS, Global Telecommunication Services, and this is the FTP, F through FTP. So this much of volume, you can see the volume of data GB per day, and this is FTP, GB per day. So after 2015, what is the changes happened into after 2015? NCMRWF procured a huge computing machine, HPC, high performance computing system. And once you have a high performance computing system in place, then you have the flexibility of receiving high volume of data, so that you can analyze the data, you can process the data to develop your initial conditions. So this is how, in general, from satellite observations, we do get radiances, that is the brightness temperature, that we convert that brightness temperature in temperature, and the winds, radial winds, and the quick scat is giving you the winds. So winds and temperature is the most important parameter to be utilized in running your model. So this is how the typical numerical weather prediction system works. You gather your observation, you pre-process those observations, then you do a quality check observations, then you assimilate those observations and develop an initial condition. So this is how you develop an initial condition. Then you run an NWB model, develop forecast, and once your forecast is ready, forecast comes in a particular format, but we have to develop a forecast in a user specific format. The development of forecast in a user specific format is called as post processing. So we do post process that forecast, and these forecasts are being disseminated to different user agencies. Different users like IMD, IITM, INCOIS, ISRO, even an National Institute of Hydrology also receives forecast from NCMRWF daily. This is how your initial condition being developed. So development of initial condition is a very huge or very cumbersome process, and it takes huge computing power to develop all those things, and keeping all those things in real time is a remarkable work to be carried out. So this is in turn, like this is NCMRWF, which I have shown you. Similarly, ECMWF, European Center for Medium Range Weather Forecasting, that also you might have, some of you might have heard. So they do run the integrated forecast system. So they started from, so the horizontal resolution starting from 300 kilometers, they have come up around 9 kilometer. Now recently they are running 3 kilometer, even 1 kilometer models. So you can see there is asterisk called as hydrostatic and non-hydrostatic and explicit convection. So when I talk about forecasting weather, most of us are bothered for weather means rainfall. What is going to happen in terms of rain? So the most important and most challenging parameter to be forecasted is rainfall. So how the rainfall is being affected? So you can see from 1983, it is a horizontal resolution of 316 kilometer. Means what? Means if rainfall has happened here at one grid, means the next information will come around 316 kilometer later, 316 kilometer apart. So will it be a, so as you all know, the rainfall has a very high variability, very high variability. If one place rainfall is occurring, you can expect after 2 kilometers or 3 kilometers there is no rainfall. That means rainfall is highly variable. So do we think that if if rainfall at one place and rainfall at the next at 316 kilometers is the better representation? No. So closer, as we are going closer in terms of grid, if our grids are being closer to each other, very fine grids, then we have a better representation of atmosphere and we have a better forecasting skill of our models. So we have traveled from 316 kilometer to kilometer scale. Now meter scale, even 500-meter scale modeling is 500-meter scale weather information is also being forecasted at city scale. So this is how the in India, how they have started. The first model developed in 1994, and that is 150 kilometer, and later it has come 75 kilometers. So 2094 to 2007, there is a one model called as TAT model, triangular truncation of TAT. So this model has been having a horizontal resolution of 150 kilometer, and the data assimilation technique is called as the 3D bar, three-dimensional variational data assimilation. So this is how you are considering the data in X, Y, and Z, but you are keeping the time constant. So this is 3D bar. So 2007, so they have increased the resolution and the horizontal resolution. So you have the information at every 50 kilometers in 2007 to 2008. But now you can see 2022. Now so down the line, this advancement, that's why I have kept one table side by side, so that all advancement happen. One way is the better representation and better understanding of the physical processes. At the same time, the computing power has also emerged from 234 megaflop to 2.8 petaflop. So this is the power of computing systems which has developed, which has been emerged, and the same time the improvement in the weather forecasting could happen. You could run the sophisticated models and 150 kilometers to 12 kilometer, and recently NCMRWF has developed a model which is having a 6 kilometer horizontal resolution at a global scale. So you might have seen that at regional scale, people, that agencies are running at kilometer scale also, but they have developed a model at 6 kilometer horizontal resolution at a global scale, and that is the coupled data assimilation technique. So you have developed initial conditions. So how do you solve those initial conditions? So one is equations is the equation of acceleration, 3D winds, conservation of mass, conservation of energy, and relationship among pressure, volume, and temperature. So mathematically, these equations are expressed as a system of non-linear partial differential equations. So you calculate these, you solve these non-linear partial differential equations by converting into the difference equation, and then you forward in time. This is how you calculate the equations. So there are two different kind of model. One is grid point model, another is a spectral model. So grid point model, you can see that you have a information at each grid. So you have equal grid spacing at that earth is considered as a mesh where you have points at equal grids. So this is how you integrate your time. Del U, that U is the zonal wind, the horizontal component of the wind. That is the west, from west to east. So that del U by del T. Similarly, minus this advection term. So this is how UK plus 1 minus UK delta T. Then similarly UK I plus 1 I minus 1 2 delta X. So this is how you are calculating in space as well as in time. So if you are running a global, that earlier I mentioned that if you are running a global model, then you don't require any boundary condition. Boundary conditions means, like here, if you will, is my cursor is visible? Pointer is visible?
Yes, sir.
Okay. So this is a picture of a global model, out of which we have considered a box. So you have an outer edge. You have an outer edge. So this outer edge, so beyond that you have not to go. So here you have boundaries. So these information also has to be provided when you are running a model on a smaller domain, like a limited area model, like a regional model. Suppose you want to run a model over India only. You are not interested to run on a global scale. Then you are running your model at a regional scale. So in that case, what happens? Then you need this information which is over the boundary. This is called as boundary conditions. So your atmospheric parameters at the boundaries should be required when you are running a regional model. This is what I was trying to show you here. Vertical boundary conditions as well as the lateral boundary conditions. So boundary conditions are in the case of regional model. So you have to specify how you are going up to the top of the atmosphere, as well as at the boundaries, what is the atmospheric conditions. So those all information you have to provide your model. So, and apart from that, what is the physical processes? Radiation processes, convective processes, boundary layer, what is happening near the surface, what is happening beyond at 1 kilometer of the atmosphere. So those all information you have to incorporate in your model. That is called as the physical processes. But what happens? There are different, the physical processes are of different scale. Like if you are running a model, then AD scale processes are also there, and the large scale processes which is also there, like western disturbances, which is large scale processes, tropical cyclone, large scale processes. So those all processes, starting from a micro scale to larger scale, you have to incorporate in your model. So if you want to resolve those process, your grid size should be of that order. but generally you can't keep the grid size of where you can target all the physical process, because there are micro scale processes or macro scale processes also. So those processes cannot be explicitly resolved. Rather, you have to take the effect of those processes at that grid and consider that this is the effect of that process over that grid. That effect of the processes is called as the parameterization. So if you consider the effect of that process over that grid, that is called as parameterization. So there are certain processes in the atmosphere which you do not explicitly resolve, but you consider that this is the value. Like if you are consider a grid, then you are saying that a relative humidity is greater than X, than 85%, then I will consider it as a rainy grid. And if it is less than 85%, then I will consider it as a non-rainy grid. And beyond that, if you will keep on putting certain criterias, so this is the assumptions, this is not actually being happened, this is the assumptions. So those assumptions are called as the physical parameterization processes. This is where small scale processes are not resolved by large scale models, because they are subgrid scale. These processes are within the grid. So effect of these subgrid processes in the large scale can only be represented statistically. So that is the process of representing, expressing the effect of subgrid scale processes is called as parameter. This is what I mentioned in the previous slide. So this is the process. This is the process are parameterized in the models. In the numerical weather prediction is the radiation transfer, surface processes, what is happening, vertical turbulent processes, clouds and large scale condensation, cumulus convection, gravity waves. So these are the processes which are being parameterized by the model. So now you can see, once you have run your model, then you want to test what kind of forecast and whether this forecast was important to me, and what is the skill, what is the confidence of this forecast. If I will say I will believe, if I believe on this forecast, then what is the skill, whether it is correct or not. So if you can see, this is three agencies I have put. One is NSEP operational model, which they every day they do run 36 and 72-hour forecast they are showing. And this is anomaly geopotential height from ECMWF, and this is the last column is the NCMRWF 72-hour forecast of wind. So you can see from 99 to 22, you can see a linear decreasing trend in the errors. This is how this has happened. So one is the horizontal resolution of the model has improved from 150 kilometer to 12 kilometer, and the better representation of the physical processes, like the convective processes which I mentioned earlier, the physical process. So it's better computation, it's better representation. So assumptions based on the observation strengthening of the network. So once you have more fine information in terms of well before time as an initial condition, so you have a better representation of the forecast. So if you will better represent the atmosphere by using the best initial condition preparation, then you have a better representation, better forecast skill. So your forecasting basically depend upon the two activities. One is the initial condition, another is the better representation of the physical processes. So in India, in all around the globe, major thrust is the improvement in the initial condition, because this is the thing which you can change by putting more data, more satellite information, or strengthening your observation network. In physical process representation, that development process, that improvement process is very slow. Physical process, because development of physical processes improvement is a very time consuming, as well as understanding of the physical laws takes time, because you have to perform lots of experience. Other than that, if you want to improve your initial condition, you strengthen your network. Earlier your observation network maybe 20 kilometer apart, now you have done it 15 kilometer apart. So you have made your initial condition, your observation network finer, you are putting lot other satellite data to incorporate it in your model. So these are things which are relatively easy rather than improving in the physical processes. So major thrust, major improvement is coming from the initial problem, initial conditions to be improved. So if you will look at the model forecast of so if you will look here, this is the IMD observation. This is the, so how my forecast was, whether the model is able to capture, model is able to replicate the monsoon phenomena, high amount of rainfall regions, low amount of rainfall regions, then we can have a confidence that model is doing good, model has good skill to represent the weather. So if you can see observation network, observation and forecast, the first panel is the observation, how the rainfall occurred, and the second panel, second top panel is the unified, the forecast from the unified model, a 24-hour forecast, and similarly this is 72-hour forecast, and this is 5-day forecast. That means this is the 24-hour in advance. If I will tell you that what is going to happen in the next 24 hour, what is going to happen in the next 72 hour, what is going to happen in the next 120 hour, 5-day forecast. So we have combined all these 24, 40, 24, 72 and 120 hour forecast, and try to match with the observation whether the 5 days in advance model was able to replicate the things like high amount of rainfall over the Western Ghats, and high amount of rainfall over this region of eastern India, where this is the very prone region of monsoon depression to be followed over here. So you can see model is able to replicate in 24 hour. Similarly, high amount of rainfall over the Western Ghats and Arakan coast. You can see model is able to replicate those high amount of rainfall over these regions, although it is overestimating at some places. But you can see even in day 5, model is able to capture the rainfall associated to monsoon depressions over this region of eastern India. Similarly, we can show you where the overestimation zones and which are the underestimation zones. So you can see the blue lines are the underestimation and the red ones are the overestimation. So you can see here the overestimation is visible over these foothills of Himalayas and in this monsoon trough region. This is the monsoon trough region we call it as. So over this monsoon trough region, you can see model is trying to overestimate, and we have already seen this overestimation is coming because because this rainfall is a replication from the strong winds. If you have a strong winds and with high moisture, you can expect the high amount of rainfall. So model is producing high winds. That's why high rainfall is associated to those high winds. So this is the reason where the model is trying to overestimate those things. But at the same time, you can see model is able to capture the rainfall pattern, which is replicated in the IMD observation as well. So we have evaluated this rainfall forecast based on the over this region, this monsoon, core monsoon zone. This is the core monsoon zone, which is mainly affected by monsoon lows and depressions. So we have tried to see the skill of the model, whether the model is able to capture over the period of time. If yes, what is the skill? So to look for the skill of the model, we have certain parameters. We have a contingency table. How do we evaluate that weather forecast was good or bad? How, if yes, then how objectively it was? Then we do consider, if your observation says that there was a rainfall and my model also says that there was a rainfall, then we do consider it's a number of hits. We do call as hits. And if we say that my observation is not showing rainfall, but my model is showing rainfall, then we say that model is giving false alarm. False alarm, there is no rainfall in the observation, but model is showing that there is a rainfall. On the other hand, there is a rainfall, but model does not predict. Then we said model has missed that event. Model has missed that event. And the fourth one is correct negative, where we say that model is not showing rainfall and observation is also not showing rainfall. That is called as correct negative. So based on these 4 elements of a contingency table, we there are certain metrics has been developed, like bias, probability of detection, false alarm ratio, critical success index. So these are the verification metrics which tells the skill of the model. So POD, if higher the POD, higher the skill of the model. And at the same time, if you are showing higher POD, then your false alarm ratio should be less. That is, the POD is the fraction of event that is correctly predicted. That the similarly the false alarm ratio, which shows that event that did not occur, fraction of the predicted events that did not occur. So it should be lower. If it is lower, then at the at the same time, you say that my false alarm is decreasing and my POD is increasing, then we can say the model is showing a good skill. There are chances then model is continuously showing rainfall, then you may have higher POD, but at the same time you may have higher false alarm also. If model is showing continuous rainfall, then it is not doing justification when there is no rainfall. Similarly, there is another matrix is called as critical success index. If higher the critical success index, higher the skill of the model in capturing those phenomena. So we have considered these red and black lines which represent the two rainfall threshold of 2 millimeter and 2 centimeter and 5 centimeter, 20 millimeter and 50 millimeter, which shows that if my model is able to represent the 20 millimeter and 50 millimeter rainfall, we have considered this is the high amount of rainfall event, because we have averaged over that location, average over that box. In that case, we have find that only 10 to 15% of events were considered, were available. So we do consider that this event is the higher amount of rainfall event over that region. So we can see the consistent 2007 to 2015 model is showing consistent improvement in terms of higher POD and lesser false alarm, except in case of 2010 where these rainfall events has shown a dip. This is all because of there is no depression during the case of 2010. Only lows were developed, but lows were high amount of lows. So if you have not that event of that threshold, but you have light amount of rainfall for continuously happening, then you are not seeing that rainfall of 2 centimeter and 5 centimeter. So your skill, you have a lesser number of points, so your skill dips down because total events are fixed. Similarly, we have considered earlier in case of core monsoon zone. Now we have considered the rainfall driven by orography. So Western Ghat and northeastern states are the two regions over India where the rainfall is because of orography. So we have seen that case of increasing PODs and decreasing FAR. So we have earlier taken the absolute threshold. Here we have considered the the percentile based threshold, 80th and 90th percentile. So here also we found the same trend, but skill over Western Ghat found better than skill over the northeastern state. Why? Because you can see over northeastern state number of observations are also very less. So model might have predicted good things, model might have predicted good forecast, but since we do have a limited observations, where on the other hand over Western Ghat we have a 796 number of observations. So this scarcity of observations also penalize the model. Suppose you might have your model has forecasted rainfall event. Since you do not have observation at that place, then you missed that event and said that model give a false alarm. But actually it may not be the case. Model might have done the correct rainfall, but since you do not have observation at that point, then you are saying that model has given already false alarm. So this is the penalizing of the model. That is the double penalty we do call it as in terms of atmospheric science. So we have seen the case of global model also in terms of Kerala rainfall, heavy rainfall event of 2021. So you can see the top panel is the IMD observations, and the subsequent panels day 1, day 2, day 3, day 4 and day 5. So you can see that rainfall valid to 17th October in 5 days advance. Model is underestimating, but you can see the peak rainfall in the 21 in the 24-hour forecast is showing, but this is again model is observation is showing high amount of rainfall. Model is underestimating that peak. Model is not able to capture the peak, but you can see the spread. Model is also able to give you that signal that there is a rainfall going to happen over that place. Although it is underestimating the rainfall, but the signal is quite prominent even in the 7 days in advance to 5 days in advance to plan your things in that way. So similarly, this is the global model. The same thing is for the regional model. So regional model is able to capture that peaks which was not present here. You can see in the North Kerala region. You can see in the North Kerala region, model is able to 24-hour in advance, more regional model, high resolution. This is the 4-kilometer regional model, which is showing that the model skill is better over this region. So, but the one thing which we talked about is the deterministic model. What do you mean by deterministic model? Deterministic model is when you have a single forecast. So your single forecast may have errors. Single forecast may have errors means you have your instrumentation error, you have your method through which you are developing your initial conditions, you have certain observations, certain approximations. So your approximation may be right or may be mismatched. So what happens in that case, if you have error in your initial conditions, since the atmosphere is chaotic, your error growth will be very growth in your the uncertainty will be more. So your chaotic nature of atmosphere will develop the forecast uncertainty. So your forecast uncertainty, how you will deal with? So how you will deal with or forecast uncertainty is the ensemble prediction system. So if you disturb your initial condition, you perturb your initial condition to have another initial condition at that time, and you run the model, in that case you can green line shows one forecast, that is deterministic, but your ensemble shows multiple forecasts. So your uncertainty has come in that forecast, any one of the forecast. This is the any forecast, all your forecasts are lying within that uncertainty. So how do we say that your forecast uncertainty, your forecast is well within the time? If your root mean square error is within the limits of standard deviation, then we do say that your forecast has the captured the all uncertainty available in the modeling framework. So you do not have one forecast, but you have multiple of forecast. So rather than saying that this is going said this the 2 centimeter of rainfall is going to occur over that location is a right word, or if we say that there is a high chance, there is a 70% of chance of rainfall over that location going to happen on that day. So this is, so if you will talk about the probabilistic mode, then it is you are beating that uncertainty. Out of 10 members, your 5 members are showing that where 5 forecasts are showing the rainfall, or 7 forecasts are showing that rainfall. So you have a confidence that 70% of my forecast is correct. So 70% is the probability of rainfall occurring over that location at that with that amount. So you have confidence that if more forecast are saying the same thing, then you have the confidence this is going to happen certainly. So this is how you can beat the uncertainty in the weather forecast. So there are different ensemble prediction system of major operational center. India is also using the NCMRWF is also using 23 members. So this is how earlier I showed you one member, one deterministic. Now we are showing that 23 members. Like NSEP is using 31 members, but their horizontal resolution is 25 kilometers. Similarly, ECMWF 18 kilometer. MOGREPS, UK Met Office, which is an agency, meteorological agency in United Kingdom. So like India Meteorological Department, IITM, Indian Institute of Tropical Meteorology, and NCMRWF. This is global ensemble forecasting system. It has been adopted from National Center for Environmental Protection, NCP and NCEP. So they are running 31 members. So they are running 21 members, but their horizontal resolution is 12 kilometers. Rather, their horizontal resolution is 25 kilometers, but they are running for 16 days. We are running for 10 days. So forecast let's it 10 days, and but the horizontal resolution is 12 kilometer. This is very high resolution in terms of ensemble prediction system, because ensemble prediction system needs high computing powers to utilize to provide the forecast well before time. So this forecast that NCMRWF, NEPS and GEFS forecast has been contributed to TIGI. TIGI is the portal where you can get all forecasts seasonal, season to sub-season. So you will get the NCMRWF forecast over TIGI, and the quality of this forecast is important in terms of all other agencies do not provide you at the native resolution where they do run their models. Only NCMRWF or maybe IMD also, they do provide at their the native resolution of 12 kilometer. So this is how, if anybody is interested to evaluate that data set for their region of interest, they can directly download the data from there, from a TIGI website. This is freely available, and then you can use for your research work or any other activity in terms of research you want to utilize. This is freely available. So this is all about the deterministic modeling, the ensemble modeling, how the weather forecast is being done, how we do utilize the mathematical models, how we utilize the numerical weather prediction models. And this is the latest technique in terms of now the 6 kilometer global model is being developed by India, and at a National Center for Medium Range Weather Forecasting, which is highest in the world at this point of time. No other country is running the model at a very high resolution of 6 kilometer. So that is still in the research mode, but the operational model is still at 12 kilometer horizontal resolution at a global scale. But there are products available at 4 kilometer, even at 1.5 kilometer, even Delhi model at 500 meters. So this much high resolution modeling is still being carried out over Indian subcontinent. So now we talked about weather. We restrict ourselves in terms of what is going to happen in next 10 days. But when we talk about climate, so climate is a long-term average of weather. Climate we talk about means what is going to happen in next 30 years, what is going to happen in the next 10 years, 20 years. So this is how we talk about the climate. So when you are running a climate model, you have to you have to consider all the earth component, like atmosphere. The main is the solar radiation and changes in the atmosphere composition, circulation. Human influences how the terrestrial radiations are being utilized, precipitation and evaporation. Excuse me. So those changes in the atmosphere, ocean, ice, snow, all those component is being utilized in Earth climate system. So how it is different than the numerical weather prediction model? One thing, since we are running the numerical weather prediction. Hello.
Excuse me, Rishikesh, please mute down yourself.
Hello. Yeah.
Sir, you can continue.
Yeah. So now you can see we have talked about numerical weather prediction model where the forecast lead time was up to 10 days. Now we do consider what is going to happen in the next 30 years, what is going to happen in the next 100 years. This is how the climate models comes into the picture. When you are running a climate model, the basic difference in climate and numerical weather prediction model is to initialize. Number one, when we were talking about numerical weather prediction, then initial condition is very important. Like which I told you, the method of data assimilation through which you develop your initial condition, that is the most important in numerical weather prediction. While when you are running a climate model, then your initial condition does not have much importance. It is required only to initialize your model. The most important thing which is important in the climate model is the boundary conditions. So you have to provide the boundary conditions at certain time of frequency, so that you always try to bring to your model beyond non-linearity. When your model is going to become non-linear, you're trying to bring it by putting some dates, putting the boundary conditions to bring to the normalcy. So NWP models require very high resolution so that the forecast can be computed quickly and accurately. The physical parameterizations are minimal in numerical weather prediction models. So the physical processes which we are considering the effect in numerical weather prediction models are minimal. Rather, we do calculate, we do explicitly resolve those processes at each grid. On the other hand, in the climate models, we do consider lot many parameterization processes into the modeling framework, because we have to run longer lead times, and we cannot keep the resolution similar as compared to the numerical weather prediction models, because numerical weather predictions lead time is smaller, while the climate model lead time is 100 years or 200 years or something like that. So in that case, you have to run the model in a quick time. A quick time means it takes years to complete the simulations. So in that case, you have to compromise in terms of resolution or computing power. If you are running a very high resolution modeling framework, even at a climate scale, then time will be more. At the same time, you need high computing power. But climate as an average picture is not going to change too much as an over that region. So if you want to represent the regional climate, you can keep your horizontal resolution as much it is allowed to you. Over the but recently, since the high computational power has been introduced, there are many organizations who are increasing their computational powers. They are using the scale of their climate model similar to the numerical weather prediction model nowadays. So this is how you couple the model components through atmosphere, land surface, ice sheet, ocean, sea ice, and then you develop a Earth system model to run and provide you the climatic information. So this is how the 60s to 2010, the complexity and the grid scaling had been changed over the period of time. You can see earlier, this is T42. Your grid spacing is very coarse, where when you are running T340, where the grid spacing is very high, very code, very high grid spacing, where you can see the coarser grid spacing. So that all credit is coming because of the high computational power is being introduced, as well as our better representation of physical processes into the climate and numerical weather prediction models. So you can see where in the 60s, very minimal information we were putting into the model: atmosphere, land surface, and vegetation and ocean. But as the time has come in 90s, we have include the aerosols and biogeochemical cycles, carbon cycles, ice sheets, and these marine ecosystems. So this is all because of high computational power has been come into the high performance computing systems has come into the existence, as well as the better representation, the research in terms of climate model and understanding has been evolved. So everyone, I understand most of you might have heard about the CMIP-6 coupled model intercomparison project. What is that coupled intercomparison project? Is that there are different global model agencies which do they run their global model, but since all global models, all global climate models, GCMs, has uncertainty, so beating that uncertainty in terms of running all those models and putting one place, that is International Panel of Climate Change, so IPCC. So all those model outputs are being shared through IPCC and through CMIP 6, through CMIP, their coupled model intercomparison project. So that what happens that we can beat the uncertainty by making these ensembles of global models. So like India also have one Earth system model, like NOR ESM, INM, EC Earth, IPSL is a France agency, ECMWF, HEDGEM is Met Office agency, CMC, NOAA. All these agencies do run their global model in a climate scale and contribute to the IPC CMIP 6. So this is the list of models. So there is one paper which we have published recently, is the fate of rainfall over North Indian state at 1.5 and 2 degrees centigrade warming scenario. This is what we have utilized. How the rainfall is going to happen if temperature increase by 1.5 degree and 2 degrees centigrade. So this is the rainfall in the North Indian states. So we have identified all these models, and we have selected 5 best model based on the selection criteria. So this is the 5-6 models which we have identified, which are showing better representation than any other. So we have seen that in this pre-industrial period, present, and the change. So what we are seeing that in 1.5 degree centigrade, precipitation likely to decrease in the most parts of cities except Jammu and Kashmir. So this is how the interpretation of the results can be done. So another thing is the questions. What you are going to address using this CMIP 6 coupled model intercomparison project? What kind of things which we are targeting? What the first is how the Earth system responds to the forcing. Forcing means how the emissions are increased by this much. Then what is that going to happen if the temperature increase by this much percentage, this 1.5 degree 2 degree centigrade. If carbon emission are increased by this much watt per, the force radiative forcing is increased by 4.5 watts per meter square. If radiative forcing is increased by 8.5 watts per meter square, then what is going to happen? These, and what is the future climate change and the internal climate variability and its predictability and uncertainties in the different scenarios, like which I mentioned. If radiative forcing is increased by 8.5 watt per meter square, if radiative forcing is increased by 4.5 watt per meter square, what is going to happen in terms of climate? So there is different things in terms of global modeling and the regional modeling in terms of climate. So like I said, if you are running a global model, longer period of time, covering more grids, then you have a CODESER model. At the same time, if you are running a regional model, then you are finer resolution area of interest than 25 kilometer or less. So what, why we do have the convective scale regional climate model, which I have mentioned. Then if you are going for a higher resolution, in that case you have a higher better representation of the atmosphere in terms of when your grid spacing is closer, or your time in, then you have a better representation of variability in terms of different atmospheric parameters such as temperature, winds, and precipitation. So now there is a huge chance that there are different agencies are running very high resolution climate modeling to understand the climatic changes going to happen in over that region of interest, over their region of interest. We also have run that model nowadays. We are also running weather research and forecasting model, and over a regional scale we are running over India. Whole India we are covering as a 27 kilometer domain and 9 kilometer over Indian Himalayan region. As we all know that Himalaya is a very vulnerable in terms of there are a lot of water availability is there. If it's a source of water over for so many places, so many regions. So if you have a better representation of climatic information, then you can estimate what is the water availability over that region, and that will serve to other regions down the line also, downstream also. So we have utilized that the model which has contributed to the CMIP 6, that is Max Planck Institute Earth System model at a high resolution model. Their horizontal resolution is 1.25 degree, which I mentioned that if you are running a regional model, then you have to force your model through a global model. So boundary conditions will come from a global model, and then you will run your regional model. So this is the two domains which we have covered is 27 kilometer and the 9 kilometer over Indian Himalayan region, and the frequencies every 6 hourly, and we are focusing over precipitation and temperature, 2 meter temperature, and we are targeting extremes, what is going to happen, whether the model is able to capture the monsoonal rainfall post-monsoon rainfall, winter precipitation, and the pre-monsoon rainfall. So we have developed using this a dynamical downscaling technique. Dynamical downscaling technique means we are taking the changes objectively using the dynamical processes. There is another technique is to provide high resolution projections and predictions using the statistical downscaling. Statistical downscaling means what? You try to establish a relationship between observation and the predicted value, and based on that you develop your high resolution data set. And the need of high resolution data set is to better representation of the variability and the better representation of the atmospheric parameter over that region, because Himalaya is also very highly variable. You do not you can see every 2 meter, every 2 kilometer, or every certain point of time highly variable. One place there is a rainfall, and after 1 kilometer you might not experience any rainfall event, because this is a terrain following effect. Terrain effect is also there. We have evaluated this rainfall using IMDA. IMDA is a reanalysis product developed by NCMRWF starting from 1979 to till date. And another observation rainfall based on India Meteorological Department at quarter degree also being utilized to evaluate whether our dynamically downscaled data set which we have developed is able to capture the variability or not, able to represent the monsoon, post monsoon, pre monsoon, as well as the summer season, that March, April, May. At the same time, the statistically downscaled data also being compared using this that whether the statistical downscaling does not require much computational power. So if we are investing that much of computational power to develop high resolution dynamically downscaled data set, whether it is worth over statistically downscale which does not require much computational power. So what we have used is for carrying out these simulation is to development for this type of data set, the CDEX National Supercomputing Systems, which is located at Trichy, and the machine's name is Paramporol. So thanks to CDEC for providing such type of computational facility to people who are not part of CDEC, but under National Supercomputing Mission, they have provided us the computing systems to deal with, to utilize and to develop your high resolution data set and for research activity. So we have seen the spatial distribution of predicted rainfall, and we are trying to see the impact of topography on rainfall. So this one is the IMDA rainfall, and this one is WRF based 9 kilometer, and the season is March, April, May, and this is the June, July, and August, September. The bottom panel is JJAS and the top panel is March, April, May. So you can see model is able to represent that rainfall, very fine scale features over this Himalayan region and over this northeastern, that eastern Himalayan region also. You can see the model is able to replicate those things. So we can say with that definitely there are some biases also, where over prediction and under prediction are also there in some pockets, but still model is able to replicate the things which I have, since the simulations have been carried out for limited period of time. As of now other simulations are going on, so we have compared this 15 years. In those 15 years we found that model is able to produce the fine scale features, which is, this is 12 kilometer IMDA, this is 9 kilometer WRF, which we have developed through dynamically downscaling. So similarly in terms of WRF and in the monsoon season, you can see the fine scale things are there, which is not in the IMDA also. This is because of, since we are running at 9 kilometer, this is 12 kilometer. So model, once you go at finer resolution, model is trying to resolve the processes at finer scale rather than the coarser scale models. So there is always a possibility when you have observation, when you do not have observation at that grid over that location, then there is high chance that model might be doing good or may or may not be doing good. But we assume, we sometimes we feel that model might have predicted the correct rainfall. Since we do not have observation at that location, we are penalizing the model by saying that, oh, model has not predicted the things which is actually observed. So this is how, this is a punishment to the models. So but we have to understand that in this region observation networks are very limited. the coarser observation network. Even at above 2000 meters, you do not find any IMD observatory. So observations are very limited over this region. So that's why we are saying that might be model is producing the correct picture, correct representation. But since we do not have observations, we are penalizing this, penalizing the model by saying that this is not captured the proper rainfall. So at the same time, if you will look at the impact of resolution, one is here it is IMDA, the top panel is IMDA, and this is WRF at 27 kilometer, another is WRF at 9 kilometer. You can see the variability resolution. You can see at 27 kilometer model is not able to resolve the variability very highly, but at the same time, if we look at the 9 kilometer where model is showing the pockets of high amount of rainfall which is present even at IMDA reanalysis, and you can see the variability is captured well as compared to observation where it is showing almost flat. And similarly, you see the peak amount of rainfall over the northeastern state, which is all present here in the observations in reanalysis product also. Model is not able to capture over this region of northeastern state when we are running at 27 kilometer as a outer domain. Similarly, if you will see over this 9 kilometer where the high amount of rainfall over the eastern Himalayan region, which is well captured over this using this 9 kilometer, which is not at all present. That peak is not being captured in the coarser resolution of 27 kilometer. So this is the power of using the dynamical downscaling. Similarly, we have evaluated by comparing the statistical downscaling and the dynamical downscaling. We have utilized MPI Earth System model to downscale that, and similarly we have used the MPI Earth System model to evaluate, and this is the NASA's statistically downscaled 25 kilometer horizontal resolution data set. You can see the resolution of the variability in statistically downscaled model. So this is the IMDA March, April, May pre-monsoon season or summer season, and this is the WRF at 9 kilometer, and this is associated biases. And the bottom panel is the MPI ESM high resolution model statistically downscaled at 25 kilometer resolution. So you can see that 25 kilometer is even this is statistically downscaled, but it is not able to resolve the variability which is being resolved at dynamically downscaled WRF at 9 kilometer. Similarly, you can see winter season, you can see the post monsoon season where the variability is not being resolved at all in statistically downscaled, which is being resolved by using the dynamically downscaled method of ours which we are using here. So this is the power of dynamical downscaling in terms of climate modeling. So you can see as the computational power has increased immensely, now there is very thin line between a climate model and a numerical weather prediction model in terms of horizontal resolution. Even the convective permitting model, even at a climate scale, it is lesser than 10 kilometer, clearly shows that there is a capability of going further higher, but the limitation comes because of the computational power. At the same time, your model also should show a substantial skill while going to the higher resolution of kilometer scale. So this is the benefit of running the convective permittive climate models for impact studies such as hydrological studies, several urban climate to understand and land use changes, atmospheric conditions over glaciers, and coupling with glacier models, evaluation of renewable energy sources and wind farm impacts on atmospheric condition. So to compute, to calculate what is the renewable energy projections, how much renewable energy capacity in future can be, what is the urban climate going to be, using these climate models projections we can estimate what is going to happen and how to plan the things accordingly. Once we know this is good, because we do not have any control to change or alter the climate, rather we have to adapt in the changing climate ourselves. So this is how we can use these climate information, high resolution climate information for different impact studies like hydrological, urban climate, atmospheric condition, floods, what is going to happen in the flood zoning, all those kind of things using these climatic informations. So this is all about from my side, which I have covered how the weather modeling has been evolved, and from 150 kilometer in India we have reached to 6 kilometer as a global model forecast. And for regional modeling we are running the regional modeling from kilometer from 4 kilometer to kilometer scales over different, even over all India. So this is the advancement has been happened over the period of time. Then starting from 1994 as a first model forecast from NCMRWF to 6 kilometer, starting from 150 to 6 kilometer. That is the advancement, and that advancement goes again because of the improvement in the initial condition, improvement in the data assimilation technique, improvement in the physical processes to be better represented, and the most important improvement is coming because of the high performance computing system, which is coming as a now in the latest, that is latest development, that NCMRWF and has utilized very high performing computer. I think it is around 6 petaflop, 2.8 petaflop to they are going to 6 petaflop. So once you have a high computational power in hand, then you can improve the weather forecast by improving the horizontal resolution, by improving the physical processes. Because if you have a high resolution computing system, then you have a higher capacity machine, so you can go for further fine resolution to deal with. So then better representation of atmosphere can be happen in when you have a high computational power in hand. Thank you very much for your patience to listen, and thank you all. Hello.
Thank you, sir. Yes,
Sir,
sir.
thank
Thank you, sir.
If
you.
any
Very
question, then I am
informative.
happy to answer.
Any questions? You can raise your hand. So I'll unmute your.
Sir, very informative session. You have started from scratch.
Thank you. Yes.
Yes, I think there is one
From
question.
Vinish, sir.
Yeah.
Vinish Nair, you can ask your question.
Yes. Yes. Good evening, sir. Am I audible?
Yeah.
Yeah, it was a very nice presentation. It was very highly informative. Thank you for the presentation. And my question is about the first part, numerical weather prediction models. So, how do you formulate the governing equation when you do this numerical weather prediction model? Or what all different processes we need to consider when you develop this governing equation for
So that is
NWP?
the Navier-Stokes equations with for fluid dynamics, which we do use to forward in time.
Okay. Okay. And is there any limitation in the time step used for the simulation of this model so that the model will be numerically stable?
Yeah, that is we do call it a CFL criteria, when the delta x by delta t. So in that case, we have to limit our time step within the five times.
5 times. That means
Five times.
delta x by delta t should be less than 5. That's what you mean?
Yes. Like we are using currently 9 kilometer and 27 kilometer. In that we are keeping 27 multiplied by 3 times, so 81 seconds.
Oh, okay.
Similarly, like, so that is the integration time. So every 81 seconds it is calculating and writing.
Okay. So, is it the case for 12 kilometer resolution?
Then if in the case of 12 kilometer, so this is not a thumb rule, but in general we do keep something like that. So 12 3 is 36.
Okay.
Yeah.
Okay, sir. Thank you.
Patil sir, you can ask question.
Very good evening, sir, and good evening, one and all. Am I audible?
Yeah.
Yes, so, thank you so much. It was indeed a very enlightening and insightful session. I would like to know about the various softwares and tools used in this uh, all calculation, designing, and describing the climate model and all. So,
Yeah,
can you please?
yeah. Actually, when you guys do not need to require to run the model, rather you might be interested to evaluate what is the performance in your application.
Yeah.
So when we do run the WRF model, so it's a certain output we do provide in terms of a control file and a binary file. That control file and binary file can be processed using different softwares. So you convert your control file and binary file in netcdf file. So are you aware with the netcdf format of the data?
No, we didn't come
The
across.
netcdf format of the data is a specific format of model output. By using the netcdf format, you can convert your netcdf data to the ASCII file, ASCII data of your location.
Okay.
So that is software called as, I do use one software called as the climate data operator, CDO. So through CDO, you can convert, and now the netcdf data can be read in Python.
Okay.
So you can utilize Python also, and you can convert the netcdf format data into your specific ASCII format of your location to analyze what change is going to happen from the historical perspective and the future projections perspective over your location, over your region. So when you are dealing with the climate data, so in general, everyone must be having understanding of handling the netcdf files. That is the particular, this is the most easiest format to understand and to evaluate the climate data. And the software which people are using nowadays is Python, which is one of the powerful language to deal with. And to be honest, this information of utilizing the Python script by all available in the Google. You will find it any difficulty you are feeling, then I want to suppose you want to prepare that seasonal things over your region, then you utilize the Python. I have used grads as one of the software to plot all those seasonal things, that how what is March, April, May, June, July, August, September. I have utilized, I have processed the data using shell scripting and through CDU, climate data operator. This is the one of the powerful tool to evaluate the model to process your data. For data processing, you can use CDO, and you plotting you can use Python. You can use even for computation you can use Python. You can use MATLAB, you can use R as a programming language. So once you have data in place, then you need to just process it. So this is the different tool: MATLAB, R, CDO, grads, Python, to deal with.
Okay. Thank you so much for your information, sir. And your session was indeed very insightful and informative for all of us. Thank you so much.
Uh, sir, I have
Now,
one
Nitin,
question.
sir, if you want to ask question, sorry, anyone else want to ask question?
Yes, I have one question.
Yeah, please proceed.
Sir, as you told in previous one project, we have used the same concept that we get the data from netcdf for a particular region. And in Python, we used to make the plots to
Yes.
understand the data.
Hmm.
But is there another way that we get actual values instead of plots? Because we found that from the plots, we have to analyze the data.
Yes.
Is there another way that we can directly get the data points in numbers?
Yeah, you can get numbers. You can get, that is what I was trying to show you. I will tell you that CDO is one of the software where you can convert your netcdf data into ASCII.
Sir,
Okay,
are these all open source
this
softwares?
is all open source. CDO is open source. And even in grads, I do use grads. You can write the data, what is the data value at latitude, longitude, and value of that particular parameter, that you can use. using grades. But CDO there is one command we do use is CDO output tab, and
Okay,
then
so
you put your
it's the
netcdf file,
uh, actual values.
then netcdf file, then it will give you the actual values.
Okay, okay. But the procedure remains same, that we have to select the data types, then netcdf format, and
And
then we have to
there is
ask for.
no need. In CDO, you do not specify the data type. You have to just provide the file, that CDO output tab, and then comma value, then space netcdf file of which you are using, and then put the output. So it will redirect your all. But the one thing, for all those things to carry out, you must have Linux environment system.
Okay, Linux environment system.
Linux environment. So you can install your software in Linux environment, that's CDO, and then from their command you use these CDO output tab. Then it will convert your netcdf data to your ASCII file of your location. Of all grid points, it will give you the value.
Okay, 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 sir. Thank you.
Okay.
Sir, very informative your presentation was. Nitin sir, you can ask question.
Yes. Thank you so much, ma'am. Kuldeep sir, it was a very nice and informative session actually. And the things which you are explaining, I'm actually working on the data sets and the same procedure. Actually, I'm having, sir, 2 to 3 questions in my mind. I have actually written it down. The first one is, sir, how to decide which GCM is used for a particular area? Do we have certain criteria that yes, we can use these criteria, and by means of which we can decide the use of these GCMs? Because in CMIP6 we are having so many GCMs, so we guys will get confused that which GCM is actually suitable for our Indian subcontinent or for our India.
Yeah, very good question. First of all, this is really a good question in terms of that everybody is interested which GCM is best for our region.
Yes.
Absolutely. Absolutely. This is a very valid question. But there is no thumb rule. So you have to rank your system. You have to, this is the same thing we are also trying to do for India. So we are trying to prepare how the standard deviation, how the uncertainty, how much uncertainty is there in that model with respect to observation. So those uncertainty we are trying, those which is showing minimum uncertainty with respect to observation, we are considering that as one of the model over that region. So you have to consider based on the standard deviation, that is the uncertainty, and there is different ways. There are different ranking methods which are available. So you have to understand for which kind of problem you are trying to decide your model. There is one model which is good for for X application, another model which is good for Y application. So you have to identify which kind of application you are trying to deal with, and based on that you have to put your ranking criteria to your models, so that you will decide, because one model is good for one application, another model is good for another application. So you have to identify what kind of application you are trying to deal with, and based on that you have to go back and look for the ranking of your models, like we have done earlier in our product, where we have evaluated CME 5 models, when then later we have identified only 6 models. So we want to see how the rainfall is going to shovel over those regions of our interest.
Okay. Actually, you have answered my second question as well, because I have entered my second question as to how to decide the rank of that particular GCM.
Yeah.
Sir, do we have any list of oceanic general circulation models for Indian coastline? OGCM, oceanic general circulation models.
Are there, but I do not have any right answer for that in terms of whether we are also using for Indian, because there are some regional model like ROMS, regional ocean mathematical simulation. The ROMS is one of the model, MOMS is another model. They have used in Indian context, these models are being utilized. But for the climate scale, how the ocean response is there, that because there are some groups who are doing the coupling of atmospheric model with the ocean model, and they are trying to
Yes,
run
yes.
simply ocean model standalone. Very few people might be oceanic services, those who are interested. But to be honest with you, I am not the right person to answer at this point of time. I do not have the
Okay.
answer of this question.
Yeah. It's fine, sir. It's fine. Thank you so much for that. Sir, another question is there in my mind. Do we have any difference between uh, ensemble and coupling? We have
Yeah.
ensemble modeling and we have the coupled model. So, what
Yeah.
is the main difference between ensemble and coupling, or both are the same one?
No. These are two different one. Ensemble is like I told you that in the beginning of numerical weather prediction, when we are running with one model and we are releasing one forecast. Okay, so this is
Yeah.
deterministic approach. And in
Yes.
that deterministic approach, in that we can couple the atmospheric model with the ocean model. That is the coupling of atmosphere model to ocean model. That is called coupling. Understand?
Oh.
So this is one
Yes.
couple.
Yes. I understand.
Understand? We are coupling the atmospheric model
Yes.
with
Yes.
the ocean model. Then this is called as coupling. That is true in case of deterministic model. Understand? Now,
Okay. Yes.
now we have one initial condition from where we are releasing the forecast. Understand? In that, there is some uncertainty in that forecast. There is some
Yes.
instrumentation error in the initial condition. There is some observational error in the initial, because there through which the instrument you are gathering the observation. Definitely that instrumentation itself has some error that instrumentation error. That is, earlier in the
Yes.
school days we used to study vernier calipers and screw gauge. You remember?
Yes.
So those screw
Yes.
gauge and
Yes.
vernier
Yes. Yes.
calipers has their own instrumentation error. We use, do you say this is the error in that? So that always inherent in the instruments. So that you cannot overcome anytime. So there always will be error. So those errors will be there. So
Yes.
that is, but we know this much is the error. But at the same time, we have to provide the forecast. So we say that this much forecast, this forecast has this much error. But how this forecast has this much uncertainty. But how to beat that uncertainty? If I say that I release one forecast with this initial condition and I slightly perturb the initial condition. I say that my temperature at this for this forecast was x Kelvin. Now I am saying if my temperature is x plus 0.01 Kelvin and my winds, accordingly my winds also gets changes. Accordingly my relative humidity gets changes.
Yes.
Just slight change in the atmospheric initial condition will give you different forecast. So when we have
Yes.
released multiple forecast at one certain point of time, then we do call is the ensembles of forecast. So so generating those forecast, if we have a multiple forecast at one time, then we do call it as an ensemble. But when we are coupling the atmospheric model with the ocean model, that is called as the coupling. That is coupling. So coupling and ensemble is
Yeah.
different. Ensemble, you have a
Yeah.
multiple set of forecast, and coupling, you are using that coupled forecast, coupled cover as one set of forecast. Your coupled forecast can be
Yeah. Yeah.
deterministic. Your ensemble forecast definitely can be a coupled forecast. Like you are forecasting one, you are releasing one forecast using the coupling of atmospheric and ocean. Similarly, you are releasing another forecast using having the coupling of atmospheric and ocean by perturbing the slight initial conditions in terms of atmospheric and in ocean conditions. And similarly, you are generating another initial condition by perturbing the initial condition with slightly higher margin or lesser margin. So this is how this slide. You see here,
Yes.
this is the analysis. This
Yes.
is the initial condition. So this is one initial condition, green one. This is the control. And now you are perturbed this initial condition and release the forecast. So these initial conditions might have developed using the coupling of atmospheric and ocean. So all these having this coupling, but all these are is together making the ensembles of these forecast.
Yeah. Sir,
Ensemble forecast.
yeah, thank you so much. Yeah. Thank you so much for that. Sir, do we have any specific methods for ensemble of this GCM data?
Yeah, you can ensembles of GCM data in like you utilize those all ensembles and then you try to beat the uncertainty using those all ensembles over that region.
There is one example at my place. I'm
Hmm.
having wind velocities, and we are having the component of U and V velocity. They are having some of the velocities are having positive value, and some of the velocities are having negative value. Suppose I just need to do the ensemble of this U and V at a particular station at a particular instant. Then I just need to do the average of the U and V component. Okay,
No,
so
no,
yeah.
you don't need
So
not to. When you are dealing with the ensemble things, you need not to do average. Otherwise, there is no point of running ensemble. So your information
Yes, that is what I am
in
at.
yeah, when you are using an ensemble prediction system, then you forget about the absolute value. You think about the probabilistic mode. So
Oh,
in your suppose you have 10 ensembles, 10 GCMs you have identified. 10 GCMs, there are some GCMs are giving U and V value X, U1 V1, U2 V2, U3 V3. Then out of you want to see what is the percentage of wind greater than X meter per second over that location, over the and that time.
okay.
Understand? Then you will identify
Yes.
out of 10 members, how many members are showing wind's velocity greater than X meter per second on that time.
So how to decide that X? How to decide that X?
That you have, it's your own choice. If what kind of, that is what I again saying, what kind of application you are trying to target. If you are saying that tropical cyclone, I want to look at the tropical cyclones. When it has developed tropical cyclones, then wind velocity should be 60 kilometer per hour. Like depressions, we do say 17 to 33 knots. When the wind velocity is greater than 17 knots. Understand? Then
Yeah.
we do say that I am interested when the wind velocity greater than X, then this phenomena of weather like monsoon depression, tropical cyclone will occur. So that you know what is the criteria of this much wind, high winds.
Okay.
That is certain textbook criteria. So you will find whether your model is able to replicate the things which is already been observed. Then you will see how many of my members
Okay.
are showing the wind velocity greater than that. Then if you're out
Okay.
of 10 members, your 6 members are showing your wind velocity greater than that, then you can say there is a 60% of chance of formation of monsoon depression or tropical cyclone since my model is showing like this.
Okay. Yes, sir. Yes, got it now.
Understand? Rather than saying
Got it.
that average picture, then again we did not beat the uncertainty.
Yes.
So you have to
Yes.
understand in such a way when we are dealing with the ensemble, then our interpretation of the things is different. I will
Yes.
like to say you as a forecaster, everybody wants to provide better and best forecast, correct forecast as a meteorologist, but that does not happen, isn't it? Forecast goes sometimes wrong also.
Yes.
But when we speak about, when we speak in the probabilistic zone, then there is a high chance to get safe, because there we do not say exactly this is going to happen. There is a chances 50%, 60% chances of rainfall greater than this amount over that region. That is what, if we say, if we have only one model, deterministic model, which says that 2 millimeter or 2 centimeter of rainfall going to happen over that location, but that may or may not correct since we are using a models. But we are using ensembles, then we can say there is a 50-60% chance of rainfall. If out of 10 members, my 6 members are showing that this much amount of rainfall going to happen over that location, then I also as a forecaster have the confidence that this is the chances of rainfall may happen since my 6 of the members are saying the same out of 10 when I'm dealing with the ensemble prediction system.
I think Nitin sir's
Yes.
Nitin sir's
Yes.
questions are
Yes,
well
yes,
answered.
Yes, ma'am.
Is it,
Yes.
sir?
Yeah,
Much
yeah.
answer. And yes, ma'am. Yes. Thank you so much,
Yes,
Kuldeep
sir.
sir and Anjali ma'am. Yeah.
Yeah, sir. Thank you.
Yes, ma'am.
Thanks a lot.
Yes. Yes, Sugri
Any
sir, you can
questions?
carry on.
Yeah. So any questions from the participants? So I think there is no from the participants. So let's move to the vote of thanks. On behalf of Bharati Vidyapeeth College of Engineering for Women Pune, I extend my heartfelt gratitude to our esteemed speaker, Dr. Kuldeep Sharma sir, for delivering such a thought-provoking and enriching the sessions. Your expertise and insights have been truly valuable to all of us. I also thank all the participants for their active engagements and enthusiasm throughout the sessions. Thank you, sir. Thank you all the participants for joining these sessions. All the participants are requested to fill up the feedback form, which are shared on WhatsApp group.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you very much, sir. Kuldeep sir.
Thank you very much. And thank you for giving me this opportunity.
Actually, we are honored, sir, by your session.
Thank you.
And totally got the information about how we should proceed with it.
Thank you very much. And bye. And good night to all of you.
Yes, sir. Good night.
Yeah. Good night, sir.